Hi, and welcome to Season 2 of the Team Deakins Podcast, a collection of informal conversations between Roger and James Deakins and a guest. We never know where the conversation will take us, so listen in and see where it goes. This episode is sponsored by Aperture and its new Storm XT52, the industry's most powerful LED point source light. Brighter than a 6K HMI and powered by Aperture's revolutionary Blair light engine, the Storm XT52 is both a tunable white light and also the brightest ever adjustable color LED. Storm XT52, unrivaled output, only from Aperture. Today we're talking about LED lights and their technology. LED lights only relatively recently have become so prevalent on film sets, and we'd like to learn more about them. To help us dive into the world of LED lights, we have Jeff Lee, Chief Product Officer at Fiilex, with us today. Jeff, thank you for doing this.
Thank you.
Yeah, welcome.
We always start with our question, how did you get to where you are today? As a kid, were you obsessed with light, or did you think you were going to do something else and then find this later? How did you get to where you are?
It's a great question. It's a chance to think back at the history a little bit. But so I guess, growing up, I've always been interested in the sciences and technology. I actually spent quite a lot of time in school. I went to graduate school studying physics and actually a lot of what we call optogenetics, where we use light to actually interact with biology. And it was only after graduate school that I found Fiilex and kind of joined the company and started working specifically on LED lights. But I've always been interested in the physical properties of light, how to shape it, the different colors, how it's used for information. And it's only more recently that we've looked at light as a tool to illuminate actual subjects. Yeah.
So when you were first working with Fiilex, was it lighting for film production, or what? Because I know Fiilex also does lights for a million other things. So did you come in working on film, or did you?
Yeah, did you imagine working in film when you were studying?
No, when I was in graduate school, we were actually working mostly with microscopes, and so we were using light to illuminate very, very small subjects. We're talking about, in our case, we were looking at worms about 1 millimeter in length. They're really small. And we were actually looking at kind of equivalent to brain activity in these worms. And we're trying to study the behavior. At that time, I just didn't think that we would, where I would end up working, building lights for a motion picture. But even when I joined this company, the company had previously been designing and manufacturing lights for other industries, for instance, indoor landscape, horticulture. And a big thing for us was actually lighting like aquariums and coral and like deep reefs. So when I joined the company, it was a bit of we had a technology, we had some applications, but we were trying to find other markets or other places where this LED technology would be useful. And at that time, one of my colleagues who came from really more of the stills world, but he kind of introduced us to film and film lighting. And I got really interested in that, and we started really designing fixtures specifically for this industry and the filmmakers.
I got to ask you, though, I'm really intrigued. What kind of lights did you use to study worms?
So with worms, you can imagine for something so small, right, in such a small field of view, traditional lights just have too broad of a beam. So really to study worms like this, you need lasers. And so we were essentially using gentle amounts of light to illuminate certain parts of the worm so that different parts of their kind of essentially the nervous system would light up, and we could actually control their behavior. It's a really fascinating field. It's this field of basically using light to study neural behavior. Yeah.
Wow.
At the time that you were doing that, how old was the LED technology anyway? I know the first time was 1927 when a Russian guy discovered it.
The roots of LED is like the light. So LED stands for the light emitting diodes, right? So it's an acronym for these three words. And a lot of the research that went into LEDs and kind of the electronics was really, most of it happened during the 60s and the 70s. Okay, and it became really popularized as lighting fixtures really later on in like the 90s. And so I think just maybe a 30-second background on this, but the first place we saw LEDs were essentially there are these tiny chips. They're about a millimeter in size. So just imagine like a fraction of a grain of rice. That's how big an actual LED chip is. And the first place we saw them was really on like simple electronics as indicators. So like the on-off button you see on your, I'm dating myself here, but like your cassette player or your CD player, that little green light, that was that's an LED. And so that's always been useful for for giving us an idea of what's an indicator, just an on-off, right? But you could never imagine this little teeny, millimeter-sized light actually illuminating a subject, let alone like a background or a backdrop, right? And so what's evolved, since then was really being able to take these little LEDs and actually pack more of them together so that you can produce more light. And in addition to that, there's also been a lot of research into creating different colors of LED because there's obviously a limitation to our application if the only thing we can produce is a green on-off, right? I mean, it's not so useful for film. So a lot of research, and actually a Nobel Prize was awarded to a Japanese researcher who was the first one to come up with like a blue LED light. So that was a big scientific discovery, and that really opened the door to using LEDs as general illumination for especially for visual. I'm sorry, for like the human visual spectrum. And so LEDs really as a technology has been around for a long time, but LED specifically for film lighting or even for interior landscape, anything like that, or architectural, I think that's relatively new within the last 20, 30 years, yeah.
Well, can you tell us how does the actual color get created by the LED, by the diode? I mean, how did the Japanese, scientists come up with the idea of blue light and create it? I mean,
so I think it's maybe useful to think about this in terms of like the analogy to this. So prior to LEDs, we've used these tungsten filaments. Like these are basically little wires that you can run electrical current through, and as they heat up, they emit light. So that's the idea. That's the principle behind up until like the 50s and 60s. You create light by heating something up and letting it burn. And then what we started to do was like people started adding different elements like boron or different halides to these flames to create blue and different colors. So you could actually add gases to different fires or flames and you could produce different light. You can also burn at different temperatures to create different colors as well. So the same idea applies to LEDs. So instead of having just one specific material give off one kind of light, you actually start adding different kinds of chemicals and materials to LEDs so that they can produce different lights. So my analogy here is actually fireworks. So the different fireworks are created by different chemical compounds that explode and burn. Same thing with LEDs. We design specific materials that have different colors. And so one of the big challenges, though, is finding these materials. It's not something you'll dig up in the rainforest. It's typically made in labs, but it takes a long time to find like just the right recipe to give you that shade of blue or that shade of green, right? So I think that's one of the biggest challenges was just finding or designing or engineering the right materials to give the different colors. And then more recently, because especially in film, like particularly for film, we tend to work with a lot of like a broad spectrum or like white light, and more loosely, I'll just call that white light. And there are different ways to create white light. You can mix different colors together. So like an RGB combined will make a white light, but there's some downsides to doing an RGB mixture. And there's also ways to make white light where you actually use some sort of LED, and it's similar to like exciting gases. Like you basically can use LEDs or the light from that to stimulate a certain material, which then emits like broader white light. And so the terminology for that is like phosphorescence. So you might have heard the word phosphor, and essentially what you're doing there is you're using typically a blue LED to give energy to a material, which is in this case a phosphor, and it's the phosphor. It actually once it's energized, it actually emits the white light. And so yeah, a lot of technology has been gone into, I would say, the engineering of the chemistry that goes into LEDs, not just the control, the electronics. It's really the materials that are really important. And it's not surprising that certain industries are a little bit. You have to be very, very particular about getting just the right recipe to get the right color. Yeah.
And
right.
Once you get that recipe, then you kind of reproduce that.
Yeah.
So you know how to make that chip or whatever it's called, and you keep it within the company. In other words, different companies have different recipes?
Yeah, so I would say back in and that's actually where our parent company got its start, was we really were making LED chips. And so we were actually fine-tuning these different recipes. And Jim, that's right. Like once you find a recipe, you try to produce them on a large scale. You make millions and millions of these chips. But as the industry has kind of evolved, what happened was that more companies started focusing on, I'm going to be the company that makes the chips. And then other companies came in and started working on the fixtures. Right. And so you get companies that work on designing chips and LED chips. And then you have companies that take the chips and then create electronics. And then you have companies who take those and actually give them a housing, give them control, put on some barn doors, put on a yoke. Right. And so that's the part that I think has been really interesting, is that the technology has been there for a while, but the technology is not really useful unless it's like fine-tuned or put in a form factor that's actually useful for an end user or an application. And so I think really in the last like 10, 15 years, it's been a lot of really great designers who are designing fixtures around the technology of LEDs for filmmaking. And so the requirements for filmmaking, the size, the color that you need, again, it's not really useful if the only color that we produce is blue. Might be great for doing certain kind of sciences, but for film, that's just not the right spectrum, right? So a lot of really, really talented designers have been trying to create fixtures based around this technology, yeah.
So at the earlier LED lights, there was always seemed a problem because there were spikes in the color. The color didn't have the light didn't come out like a tungsten bulb the light emits that has a sort of rounded curve, if you like. LEDs had spikes. And still today, if you get even a soft light, a panel light from one company, it might not necessarily match the light of another company. Although light is a very defined spectrum, white light, right? It's a balance of the colors that make up white light. Even though that's defined scientifically, that it doesn't seem to be a standard within the manufacturers of LEDs, because I haven't used that many LEDs, but I've experienced using panels from different companies and have them not match.
Yeah, that's a really good point, because that's probably one of the practical challenges with LEDs. And this is actually related to, James, your question earlier about like the different recipes and the formulas, right? So different manufacturers will use different brands or even concoctions, if you will. I'm just going to simplify and just call them concoctions of LEDs. And so just because a chip is, Roger, going back to the spikes, the reason why there are spikes is because there is in some cases, a blue LED chip, also with a red LED chip and a green LED chip. So those three colors combined, they make up a white spectrum. But if you actually look at the spectrum in detail, it might give the same CCT, color corrected temperature, but it's actually composed of these three different colors. Whereas like a tungsten bulb actually has a broader spectrum. So they both produce white light, but one of them is composed by a broad spectrum and the other one's composed by these three more discrete spectra. And there's some pros and cons to that, but one of the biggest challenges again is going back to why LED has been challenging is for tungsten, the material is pretty standard. It's tungsten metal, that's pretty standard. But LEDs, there's dozens and dozens of different manufacturers, right, who design slightly different LED chips. So we could call it red, but really the red might be shifted by a little bit and it would have a different output. And I would say I really like to use like cameras and monitors as another example. Different manufacturers for screens, and they have different concoctions too. And so what we end up having to do with a lot of like, for instance, like cameras or even with monitors, we have to do color calibrations. So the idea is that even though they're manufactured by different companies, we can use some kind of color standard or calibration to at least, kind of normalize or again, kind of unify the color space. And then with LEDs, I think recently there's been a big push to do that. I think that's a great idea. Not necessarily, to get all the manufacturers to use the same chips. That's probably not the right idea, but it's basically to get people to, given the chips that we have, given the different spectra, can we at least have certain settings where we can all agree that this is the correct color, or at least this is the calibrated color? I think that's important, and it's an important step to move towards. It's quite challenging. Getting everyone together in the same room to decide on this is challenging, and then it's with everything. You need a lot of control. The electronics are complicated. The temperature matters. There's a lot of factors that go into it.
Right. But once this is probably off the main flow of the conversation, but I just wondered if
that's your
no, I just wondered if like if you're using an HMI light, for instance, or a tungsten lamp, but not the actual filament, they would over time change, and they would lose their color fidelity. The same as if you use a tungsten lamp and put a gel on to color correct, the gel would get hot and the color would shift. But you don't get that with LEDs, or do you over time get any loss of fidelity?
That's a really good question. My short answer to that is yes, we do see that in LEDs. It's a matter of time, and it depends on how well the manufacturer is correcting for that. So to give one example, I do think it's the case. What we're doing with LEDs and we're doing with filaments, whatever it is, we're putting energy into some kind of material, and that material emits light. Right. This is something that you can, every material out there has some kind of wear and tear. In the case of tungsten, it's designed to burn at a very hot temperature. Okay. But what happens when it burns at a really hot temperature? It actually starts to emit some particles that deposit on, like if you see it on the globe, you start getting some frosting and little specks. That is degradation. It takes a while for the degradation to happen. If you run it hotter, it'll degrade faster. But that's essentially what's happening. I think broadly speaking, the material is starting to, I don't want to say wear out, but it's starting to change over time because you're dumping so much energy into it. LEDs are no different. As you're running the LEDs, as they get hot, they also will start to change. Chemically, they're starting to change. There's a lot of mechanical stresses, a lot of things are happening. And so even with LEDs, you'll actually start to get shift. It's just that a lot of manufacturers, to get around that, what they'll do is they'll run LEDs at a cooler or a lower power so that it degrades slower. Or another thing you can do is that you can actually have like LEDs, there's some properties of LEDs, or you can have different colors. For instance, you can have warm, if you're worried about something shifting green, that's a very common example with LEDs, is that as they age, they start to shift green. Mm-hmm. We're very big on making sure that doesn't happen with our fixtures, but the stuff I have in my house, after about 3 years, it's not the same as when I first installed them. Yeah. But as they shift, what you can actually do is you can actually have other LED chips next to those chips that compensate for it. So example, if you know that you have chips that are starting to shift green, you can actually bring in a little bit of magenta in other chips to kind of level it out. It's still a form of degradation, but it'll prolong the life of your fixture. And so that's kind of the workaround. But inherently, all materials will wear out.
But from a practical standpoint, if you're using a light on set that you've gotten from someone and it is getting older, how are you supposed to compensate for it or even notice it?
Yeah, that's also practically a challenging question because we see that too. I do think that I'll go ahead and say this way. Unfortunately, a lot of the lights are not designed to be used for long periods of time, meaning like the life cycle of these lights, many of them is just not the same. With the HMI and tungsten, you have a fantastically built, sturdy housing, and you know that there's an element that wears out, and that's the bulb, right? Generally, it's the bulb that wears out. You replace the bulb. We accept that. People even keep logs of how many hours the bulb is running if you're really particular about it.
Especially HMIs.
Yeah, especially with HMIs, right? But with LEDs, there's this assumption that they just last forever. I mean, even when you go to the home improvement stores, they'll say 50,000 hours for LEDs. That's 50,000 hours of illumination. It's not 50,000 hours of the correct color at the correct intensity, right? So it's a little bit misleading there. And in our industry, we care a lot about these details, right? A little bit of a little bit of green or a little magenta shift. It actually matters a lot to us. And so I don't really listen to those numbers that much. It's really, I think inherently LED fixtures, once you start getting to the point where they start to degrade, there's not much you can do about them except for replace them or replace the actual, if not the whole fixture, at least the engine or the LEDs inside of them. And in many cases, it's not practical to do so because they're made in such high volume. And the life cycle is so quick for a lot of manufacturers that in many cases, it makes more sense just to switch them out. James, you might notice this basically. I think with anything, if it requires a very sophisticated meter to see what's happening, then I don't want to say it's not important, but it's probably less important. I think we start to notice these things because they're obvious that one can see by eye. So, or on the camera, right? But if we're looking at histogram, then it's like a teeny little blip there. that might not be that important. It's when things really start to go south that we should be more aware of them. Yeah.
Right, exactly. I mean, the thing is with an HMI bulb, I mean, after so many hours, you could see it changed color temperature. You get a lamp with a new bulb, and side by side, you could see it. You didn't have to use some fancy meter.
Exactly, yeah.
But it's interesting because when we talked to Donald and Greg, a DP and a makeup person,
artist,
about how continuing a scene later, they came in and he had the same makeup on and they looked different. It's also very possible that maybe it's slightly different lights that he's using, but from the 2 times. But
I think that's just a given that anytime you start a shoot, you want to check your lamps. And so it's interesting to know. I mean, LEDs are not that old at the moment, but some might be, some from certain manufacturers that have been, Harry's producing space light or, sky panels for years. So, they may have changed color by now. Who knows? So it's always best to test it yourself before you start, isn't it? It's interesting you say about the degradation and the heat. So cooling the LED light becomes really important. I mean, you look at a lot of lights, LED lights, and there's quite a noisy fan, or there's quite a noisy cooling system in some of them, just trying to keep, which always surprises me. You've got this sort of high technology thing.
It's a bit counterintuitive
it's unexpected
for film.
To have, it's like, it's not a brute arc, is it?
Yeah, that's probably one of, if I were to say, one of the biggest challenges to the growth in LEDs is heat. And okay, going back to like tungsten, those are designed physically by nature to burn very bright and very hot. Okay, so that kind of the higher temperature at which you burn something, kind of the bluer or bluer the color. LEDs are not designed to be hot. They're actually designed ideally to be cool. And then the color that comes from it is designed by is from the materials. It's like the choice of materials itself. And if I were to go back and think about why LEDs have evolved the way they did, again, we're talking here about the technology, but the actual fixtures that came in, it's not so surprising that some of the earliest lighting fixtures were not Fresnels and ellipsoidals, and the LED ones at least. They were panels.
Right.
And part of that was because, again, with LEDs, you need to actually route a lot of electronics. Like every little chip needs to have some wires going to them, and you physically need space for that. And so panels make sense for that. But it's also because when you're looking at a panel, it's actually a much larger source, right? It's a bigger area. So the same energy is spread over a larger area. And so in terms of cooling, you have less localized heat. And so that was, in my opinion, one of the reasons why LEDs, when they first came out, like for fixtures, actually for film, they were in the form factor of a panel. More recently, and it's sort of the approach that me and our company took, was we wanted to make something that was much smaller, where it's more like a point source, right? More closer to what we had in the HMI and tungsten days, where it's again smaller point, and you could actually fit it behind a lens as opposed. There's no way you're going to put a Fresnel lens in front of a giant panel, right? But being able to do that involves solving this problem of heat. How do you get heat away from these chips, right? And one analogy I like to draw here, again, has to do with actually it's not from lighting, but it's actually from processors or chips. So in the current day and age, we hear a lot about fast processing, GPUs, AI, all these things, right? There's these very, very fast chips that do a lot of computing. Everything you do on the computing side requires energy. The more you do, the smaller you pack it, the more localized energy it is. And now one of the biggest challenges in this entire field, I'm sorry, this is a little bit of a tangent, but I think it's something interesting, is
it's interesting.
As this technology develops, like we're fitting more and more technology onto a smaller package, right? But that means now that there's more heat and more energy being used in a smaller package. It's really difficult to get the heat out of it, right? And so what's holding back a lot of chip development is not just like making things smaller, it's about getting heat out of them. And so the same thing is happening with processors and microprocessors as with LEDs, where heat's a major concern. I think that's one of the biggest problems. And Roger, you bring up a good point about the fans. Fans are really designed to cool what we call heat sinks. So you have an little LED chip or something, and it's usually like glued or some sort pasted to a larger piece of metal, and that's like a heat sink, right? Like a radiator, essentially. And then fans are then designed to kind of cool down the radiator. So one of the challenges is getting the heat from the chips to that radiator or that big heat sink. But most efficient way to cool it actually would be to try to get the heat out of the chips. I mean, basically, I'm trying to say that it's typically bottlenecked, or it's probably limited by the ability to get heat out of the chips. And so if you can design certain fixtures that can cool like closer at the chips, that's ideal. And in terms of retention, like longevity, things like that, one of the things you'll notice with fixtures is that the hotter you run the LEDs, the higher the power, they actually degrade faster. So I mentioned earlier that a lot of manufacturers will just choose to run LEDs at lower power because and that's generally true. But another thing that you can do when I'm talking about compensation is it is possible that if LEDs, as you run them longer and for hotter, they start to degrade differently, you can, again, I mentioned that you can maybe compensate it for adding a little bit of the other color, but you need to be able to measure how a light is degrading, right? If everything required you to meter this and then go to a computer and then recalibrate your LED and then meter, I mean, that's just not feasible,
Sounds
right?
Great.
So what certain manufacturers are doing, and ours included, is we're actually starting to measure the temperature, not at the heat sinks, but actually at the chips, where the heat matters the most. And so what we're doing is we're actually doing this kind of feedback where we're measuring the health or the kind of the spectrum or the quality of these LEDs over time, and we're actually compensating for that at the chip level. So it's a little bit harder to do, but that's sort of how some manufacturers have been able to maintain like kind of a more consistent spectrum through a longer
So when you say you measure it at the chip level, then does the measurement determine how much cooling you're putting in?
Good question. Yeah. So what we try to do is we try to keep the LEDs in some kind of optimal, like just like an optimal band or a window of like a good window of operation. And so as long as we're in that window, our color doesn't shift. And then once you go beyond that window, then bad things start to happen, right? And so it is the case that sometimes if we measure that our chips are getting a little bit too hot, we'll actually turn up the fan speed on our fixtures to compensate for that. Yeah? And if we notice that the chips are actually running at a very low temperature and we don't need so many fans, we'll actually automatically turn them down. Of course, now as a manufacturer, I prefer to just have those automated so you guys don't think about that and just focus on what's in front of the camera as opposed to behind. But there's always the option to control it yourself if you really want to. But I think the idea there is like the fans are really not a plus; they're kind of a necessary thing to have. It's a necessary evil that you have this, you got to have that. That's one of the biggest challenges moving ahead is heat.
So clarify for me then the design of a Fresnel lamp. I mean, your Q5, Q7 series is a wonderful equivalent to a Mole Richardson 1K Fresnel in my mind, except that you got the ability to change color and and intensity and all the rest of the stuff that come with LEDs. But what we at one point early in the development of LEDs went to the Aries manufacturing site in Germany. And they showed us the problem of producing the equivalent of a tungsten bulb, a 1K bulb or something, a point source to go in a Fresnel lamp. And so you've got the problem of the intensity of the light. So it's the number of diodes you stack together, right?
That's right.
In a confined space. And the more intense you have them, the higher output each of those diodes has with the hotter it gets, then the more problem you have with cooling.
Yeah,
is that right?
I think your observation, whoever told you that, really summed it up correctly. Yeah, that's it. I mean, we've seen panels for quite some time now because again, I think it's generally in terms of engineering an easier problem. In order to make a Fresnel, you need to put your light source behind or in front of the lens, however you look at it. And then the lens itself has to be large compared to the source itself. Okay, that in order to get this kind of converging effect of the lensing effect. So to really get the quality of a Fresnel, you really need to start with what's more like a point source, which we had for the longest time with bulbs and tungsten filaments and HMI, things like that. And exactly that's it. I mean, the challenge of being able to cool LED chips when you pack them so densely is one of the biggest challenges. And then on top of that, because we needed to do things like compensate for color shifts and have different color tunability, it means you have to now pack different color LED chips, all with compensation and calibrations into that tiny package. So this becomes a very, very challenging problem. I think the industry has grown significantly since kind of the mid to late 2000s. But yeah, this continues to be a big challenge, and it's actually, Roger, I think it's what is probably limiting the development of larger fixtures. I mean, we get that question a lot. What's next? What's the bigger? And I mean, we're always working on things in the background, like what you see in the market. We'll always have something else in R&D, but it's taking longer and longer to develop these bigger lights because it's just, I think, technically just becoming more of a challenge. And so what we're starting to see a little bit more of is actually companies that are doing things that I think closer to like the Dinos or the Maxis, where you can take sources and you can kind of tile them together, right? And so, I mean, again, that gives a lot of output, but it's really not a Fresnel, right? We're still talking about something that has multiple sources. To really do a Fresnel, you really have to put all the chips or the LEDs behind one single lens. That's the key. And so if we're looking at the evolution of LEDs, and it's something that I was pretty excited about a couple of years when we brought out our first LED-based ellipsoidal or LECO, was that's even more challenging problem, right? There we actually have to now fit a light source behind a polished piece of glass where all the edges and the aberrations matter, right? That's an even harder problem. But I'm pretty excited about now the industry.
It must be another an increasing problem is that you've got to have different color diodes.
Yeah.
And so if you've got a Fresnel or any kind of lens in front of it, is that not going to reflect any imperfection in the layout of the colors?
Absolutely. Yeah. So what the Fresnel lens is doing essentially, I like to think about it as really a camera in reverse. Okay, so what's happening with the camera? We're taking some subject, we're taking light, and we're collecting it using a lens and then projecting it onto a sensor. Okay, and what we're trying to do is we're trying to capture all the fidelity of the subject and map it to the sensor. Now flip it around, which is what a LED fixture is. It's instead of a sensor, it's a light emitting diode, and it's projecting light out of that, going through a lens, and then being again projected or thrown onto a subject. So same thing, the lens is working both ways. It's maintaining fidelity, right? And so with LEDs, if you have, in this case, like, these are typically RGB mixes for different colors, those little RGB patterns will actually appear on your subject if you don't treat it correctly. And so I think it's all about relative scale, where if you're far away enough from any fixture, it looks like a point source. You could take a blue or red, like different gelled fixture, if you take it far away enough, by the time it reaches you, it's so small relative to you that it basically looked like a point source, right? As you move closer and closer to closer, you start to see, oh, here's a red fixture here, there's blue, there's a green. And the same thing is happening with LED chips. The tighter you can squeeze these chips together, the more it looks like a point source, the less you have to worry about aberrations and things like that. And so it's all about going smaller, smaller, smaller. But then again, we run into the problem of heat, right?
Okay, I mean, this probably is obviously a silly question, but it seems like you're kind of basing a lamp on what was basically being manufactured for, I don't know when was a Fresnel lens invented? I mean, probably 70 or 100 years, I don't know.
Yeah, plus originally used for big lighthouses. It was actually the.
Oh yeah, right. Yeah. Of course, even much further ago. Yeah. I forgot about that. I was thinking about film lights, but of course it's not that. But I mean, my point is there no alternative? After all this time, has not anybody come up with an alternative? Because again, part of the problem is you're encasing the LED in this structure with a lens on front, and by definition, it's not got air going around it. So when there's we were shown by a scientist this LED panel that, well, it wasn't. It was trying to create a point source, but it was like a circle that was about 4 inches wide, which was as small as they could get. But they couldn't run that in enclosed space at the time. That had to be in open air. So you could see the challenge. So is I mean, obviously an open face by itself it creates a different kind of light, and that's part of the tools of a cinematographer. But is there no alternative when you design an LED chip to actually putting it behind a Fresnel lens?
So I think this gets into a question of what kind of fixtures are suitable for LED technology, or what should LED technology be applied to. And so again, for the longest time, I think the LEDs being applied to panels has been that's been quite fruitful. It works out well. The fact, the size, the heat is all. as we get smaller and smaller, it is, even though I'm obviously biased since we work with LEDs, it is possible that LEDs are not the right light source for everything. Like going back to, this is my earlier days when I was doing microscopy, we weren't illuminating with LEDs. We were illuminating with lasers because we were looking at subjects so small under such small lenses that we really need a point source and a very directional source. And that's just something that's not an inherent property of LEDs, or, of course, there's other trade-offs. And so I do think that, and there are some manufacturers who are working on using sort of laser sources for different kinds of optics. So I think what we're running into now is like, we've spent some time with the LED industry figuring out like what kind of fixtures are suitable for LEDs. They're open face, or they're in their panels, or Fresnels and Legos. I think there's still a lot of space there where we can do a lot more growth and optimization, but we will probably eventually hit a limit, as we are with kind of the larger fixtures, where LEDs themselves might not be the best source. And I don't have a good idea of what would replace LEDs in those applications, because we have now become, I don't want to say spoiled, but it's been pretty nice to be able to dim things the way you want and change colors and IP rating, that even if there's a new technology that comes out, it'll probably come with a few negatives, which it's not clear that filmmakers will be willing to make that trade-off.
Yeah. I think the one thing I miss when I've used LEDs that I missed from a tungsten source is that you can dim it down and it will warm up as you dim it down. But to do that with an LED requires quite a bit of programming.
Yeah. Those are the things, Roger, the programmers and the people at the board are purposely trying to calibrate out. So it's just the same because they're maintaining.
Yeah, right. Of course. But when you're doing sort of firelight or candlelight or something, and we want it flickering, it's really nice when the lamp gets warmer as it goes dimmer, and then, it just goes up and down. And I don't know. It's just.
That's great. I have a. That's a new idea for my intern, so I'll work on that.
All right, there you go. So, can you? There was one expression, dense matrix technology. Is that what we've been talking about then?
Yeah, that's a. I don't want this to be a shameless plug, but that's the term. That's what our company coined. Our technology is the ability to pack chips close together. But really, the idea is being able to, the word density is key. The matrix just, it's because it's a grid, or like a matrix of other chipsets, and then and the array, which actually means a very similar, it means similar also, like an array of elements or array of chips. Yeah, that's the name that we use for our technology. But really, it's this idea of being able to pack chips so closely together that it looks more like a point source, or shall I say quasi point source, and then also being able to like change colors and things like that. Yeah. And it's really the engine or the source that goes behind everything that we make. So that's why we tend to focus a little bit more on hard lights, because that technology, when you pack them in a source, it's just more efficient to use as a hard light. Like you could make a softer light out of something like this. You could put a softbox in front of it, and you can silk things, you can bounce them. But in terms of, that's again the trade-off. Some people want that quality, or some people want to start off with, let's just start with a larger source panel. I mean, it's already closer to what we want at the end. Why don't we just start with a panel? So I think that's a choice, yeah.
But I would think, though, a lot of people would also prefer to start with the harder source, because it's something that they might know that they've used tungsten-wise before, and then they can soften it down to the degree they want.
So I kind of came a little tangentially into this field, and we actually connected when we first started out. We connected a lot with a lot of TV shows who were using a lot of tungsten, right? I mean, there were features obviously who were a little bit, in commercials that jumped to LEDs, but a lot of the TV show tungsten guys and girls, they really liked our lights, because they had, and I remember very, very clearly when we went to do a demo one time, and they're like, "Wow, your fixture has the feel of a tungsten." As like this soul of a tungsten. And I thought that really stayed with us, because we put a lot of technology into this fixture, right? But our goal was to build a tool that filmmakers already know how to use and are familiar with. It wasn't to reteach them something, right? It was to make something that they already know well, gives them quality they want, but we just added some more features, or we do it with more modern technology, which has other advantages. So I thought that was that for some funny reason we always connect with the people who were turning knobs and kind of using, I don't want to say old school tools, but there's something about that.
Like me, for sure. Yeah. I mean, I like that. A panel light or soft light, there's no way you can focus light. Even if you're bouncing it, I like to bounce with a Fresnel because I can control the size of the bounce by just spotting or flooding the lamp, which is something that your units do. Have you noticed with the development of LEDs that people have tended to go towards more panels and lines of LEDs, more soft light sources?
Manufacturers, you mean?
Well, no, cinematographers. Manufacturers and cinematographers. They maybe. Has it influenced the way you see people lighting on a set, do you think?
That's a great question because I think I don't want to say it's a chicken and egg, but filmmakers will use what tools are available. I mean, we'd all want everything to have all the specs we want, but it's the reality is that if there are a lot of panels available and they have all these advantages of LEDs and it's in many ways greener, or it's in terms of energy conservation to use LEDs, then that might be the choice. And that in itself might dictate or kind of sway the kind of lighting you end up doing, right? And so that is one of the challenges with LEDs is when they first came out, it was generally a soft light, right? It was generally panels. And so I think people were really jumping on the advantages of LEDs, which I think are all very true. But because at that time there was only one sort of form factor or one type of fixture, LEDs became synonymous with soft lighting. In reality, I don't think LEDs are technology. It just so happens that the earlier fixtures were soft lights. But at that time, and actually for us, it became in developing Fiilex and our fixtures, we had an interesting approach because we've always been focused on hard lights and Fresnels and Licos, and we'd go in there with LED technology, and everyone would be shocked, like, wait, how are you able to cut? How are you able to shape, right? This is not an LED, right? And so I think that's the part that it's changed with the technology and the approaches.
When LEDs first came out, it was primarily film that was being shot, right? At that time.
Yeah.
And then we've come on more to digital. Is there a difference in the way that LEDs react with film versus digital? Because, for instance, when we were starting with digital, we would have to do a lot of tests on neon because it would pick up different colors and we needed to know. So is there a different way that LEDs react to digital versus film?
So ultimately, like whether or not you're digital or you're film, you're still capturing. We're capturing light, but I think at the very beginning of our when we were chatting, Roger mentioned just this idea of spikes, right? These spikes in the spectrum, right? And these become very apparent in digital because if you think about what's happening on a digital camera, it is also composed to get color. It is also composed of RGB pixels, and so there is a lot of purists will be upset when I say this, but there's something about discreteness and continuity which in my opinion, what separates out the analog film world from the digital and the LED world. And what I mean by that is when we're shooting film and we're using broadband sources, it's generally continuous spectrum, right? It's kind of flat, not necessarily, but at least it's kind of smooth and flattish, right? But once you're dealing with LEDs, you're starting to deal with like some form of spikes, okay? And then the camera sensor that's capturing the LED also has some form of spike, right? And so you have things that are discrete being captured by things that are diffuse, and you're just kind of layering this on. And it's not so surprising that we'll see what are called artifacts, right? Basically things that arise from the discrete nature of the sampling. And so I do think that there's a big difference, and which is why you need to calibrate for. The upside to this is because the detectors now, I mean, I'm not saying they're not sensitive, but because of the discrete nature of them, you can actually fine tune them a little. Yes, there's like, different kinds of films from different manufacturers, but on the digital side, you can actually do a lot of calibrations for the camera that kind of matches or compensates for the LEDs. And that's another thing that I think a lot of manufacturers looking at doing is actually having, like we mentioned earlier, why is it that different lights look different on my camera or on film? Well, what you might be able to do is, depending on what light is being used, you might be able to program the lookup tables on your cameras to kind of match the kind of lighting you're doing there. So that's, and I think that's a direction that a lot of vendors are looking at,
But right now, you might have to do that for each different manufacturer. are you saying?
Yeah, or we could try something which people push for, which is to get all the LED manufacturers to follow a standard, and that there is a big push to do that. But the challenge with that is just because the number on the screen says that I'm at this, what's commonly used right now is the CIE 1931 XY, even though my fixture says it's at some 0.27 or whatever it is, doesn't mean that it's actually outputting that. Just there's this, the number says it, the screen says it, but whether or not it's actually outputting that is a different issue. And I don't want to say it's an easy problem to solve because we mentioned earlier heat and calibration. It's actually challenging. But once we get into the industry, we're in a situation where everything is just a number and we have to trust the fixtures and the cameras completely. I do think that's a little bit dangerous because it's so early on. Yeah.
Also, if you could just explain to people, because we keep referring to spikes, so maybe you could just explain that.
Yeah. So
people can follow.
Yeah.
Along.
So spikes. Why do we see these spikes, and what is it? In what way do we see? So obviously, when we look at a light, we're not seeing something zap our eye like a spike. What that refers to is if you take any sample of light and then you basically plot it, so you draw sort of the intensity versus wavelength. So if you look at the spread of the different colors. Okay, so let's say it's typically shown from kind of blue on the left to like reddish on the right. If you look at the spread of the color, what it tells you is that if the spread is very uniform, meaning every amount of red is the same amount as every green, blue, and so forth, that what we call is very uniform, okay? Then you can have situations in which you have a lot more red than you have blue, and that would be kind of skewed towards one way. And so basically we're referring to like the shape of the spectrum when we plot intensity versus wavelength or color. And spiky for LEDs for the longest time, we've had these spikes because they've been composed of these R, Gs, and Bs. Okay, so they have these. If you actually look at a camera sensor, it's the same idea. Camera sensors have different, instead of like LEDs are emitting a certain spectra, camera sensors, the RGB pixels on those are actually receiving, or they're sensitive to different spectra. So the blue sensors are designed such that they have a spike at the blue, the R has a spike, and so forth. And so it's really if one thinks about cameras, the LEDs are, I think, just it's very similar, but just outputting instead of absorbing light. Yeah.
Yeah. Well, it also explains too that why cameras, if you shoot on two different digital cameras and you bring it into post, sometimes you have to struggle to make them match the color. Yeah. Basically, because they're responding to the color differently, a little bit differently.
It is interesting though. I do want to maybe useful to think about. So we mentioned the idea of calibration. If we take a look, this gets into when we say that something looks the same, it's under what context? It's a perceived sameness or likeness. So if I give you a screen that has a very low resolution and it cannot capture any of these details, then I could take any input, it'll probably look the same. But if I start giving you a screen that has high resolution, higher fidelity, then I'll start to see these differences, right? It's like the same thing of looking at low resolution versus HDR and then 4K and so forth. I would say the same applies to color. In the case where, right, so instead of looking at something spatially in terms of resolution, let's think about resolution in terms of resolution of color, being able to separate different wavelengths or different color bins. Coarsely, if we only have RGB pixels, you can essentially tune them such they have similar sensitivities and you can do some calibrations. However, what will happen is because you only have these three bins, you actually lose a lot of information. And the question then is, if I lose this information, does it really matter? Well, if you're displaying it on something that doesn't reproduce a lot of this information anyways, it probably doesn't matter, right? But if you're using it on a format or on some media that actually is able to capture all this detail, right, you're actually losing information. And so I think there is a limitation to these RGB pixels. I mean, and it's just the same reason why for cameras, for LED fixtures, you're starting to see more manufacturers bring out RGB, amber, cyan, and different color chips. But we haven't really seen that on the camera side yet, right? That's actually a huge challenge itself. But we're already starting to see that on the lighting side. But it's for the same reason, right? We're trying to be able to, instead of having 3 spikes, let's split it up into 4 spikes, 5 spikes, until you have so many little spikes that you actually can make up a really fine resolution. There are scientific tools called spectrometers and stuff like that that can do that. It just hasn't been brought to the camera world yet. Maybe in my nephew's lifetime, but
yeah, I mean, then you've got a huge complexity if you're trying to create a Fresnel lamp.
Oh yeah, And
with 5 different colored chips or diodes or whatever you want to call them.
and imagine the data size, right? Like just going from just monochromatic versus to black and white versus color images, right? You now have 14 or 16 bits for every color. Now that's for 3 colors, then 5 colors, and more. It's huge, right? So I guess the point here is that, and I think it's useful to think about, is whether or not the fidelity really matters to you or how you're displaying it, right? It is the case where sometimes we can, because the camera doesn't pick up these things anyways, then we don't need to illuminate. There's no point in illuminating anything with infrared if the camera doesn't pick up infrared anyways. But if it's a detail that you really care about, then yes, we do. Then the infrared does matter, right? So I think whoever's the operator or the user really has to think about like what part of the spectrum really matters and whether they're okay with information being lost. Because when we're doing all these transformations, right, we're taking something that has these colors and then we're sampling by things, but it only has in itself a subset of colors and then a subset of colors, and then the data types and transfers and what's going through the DIT also has its own set of colors. Like things are potentially lost or even manipulated along the way, potentially for good reason, for size or because they want to do something purposely in post. But it is the case that through all these different transformations, we tend to lose a little bit of information, and it's up to like the user to think about like whether or not that's okay.
Yeah, it's also not to say that film was that much better, because it's you're still restricted to 3 layers of emulsion. You're not capturing everything that your eye that's transmitted to your eye, are you? And even your vision doesn't take everything that's been transmitted in the spectrum either. So here we go. Everything is a compromised reality out there we're not really aware of at all. We never see the full spectrum of light, do we? Let's face it, no. Or the full spectrum of energy, because that never ends, does it? We only see a narrow width, and it's kind of interesting that cameras are, part of the problem is they might be getting more into the, ultraviolet or infrared that actually we're not aware of.
Well, and also you're going to see it on the television.
Right. You're going to see it on the television, and then that's a whole nother different.
That's all set
they're
differently
reproducing it with the same narrow.
Why are we trying so hard?
I just wanted to go back on the sort of Fresnel lamp thing. I mean, it's part of the problem because everybody, as you say, now we're all kind of, we don't want to give up the fact we can change the color by dialing it, or on our kind of laptop or iPhone even, program it in. I mean, if you were just, no, it's probably nonsense, really. But why use 3 colored chips? If you created a single colored lamp, and then is there no way of correcting it? I don't know what I'm talking about, really.
That's okay. But Roger, I think that's a good point. It's like there are in terms of so the 3 color chips is just how they started, but pretty much all the manufacturers now for LED lighting that do color are now using 3 or more colors of chips. It's like you're saying, they're trying to add in more colors. Part of it's so they can get more saturated colors, like so you can get like ambers and things like that. But it's also, like we mentioned earlier, it's to fill in that spectrum, just so it's less spiky. And so
But what's the difference then? Early days, and haven't really seen them lately. There would be you basically have 2 colors that would be mixed. There would be a tungsten and a daylight.
Yeah.
Right? Yeah. And then you could switch between tungsten and daylight. This was early days shooting film.
Yeah.
So that seems to have gone by the wayside.
Because the spectrum you get from tungsten, the spectrum you get from daylight, you can actually create, for the most part, those 2 spectrum using mixtures of RGB and RGB amber chips anyways. And so then a lot of manufacturers have decided that let's just go away, do away with what they would call traditionally the bicolor, just like the 2 colors of daylight and tungsten, since we can create that with a full color spectrum, of spectrum of different chip. And so I think that is the direction that a lot of manufacturers gone in, is basically to be able to do full color. And we've done that too, where we can go full color, but we can also produce different white light. It is not equivalent. I will not say that they're equivalent. Having a tungsten phosphor and daylight phosphor versus creating them using like mixtures of different RGBW and cyan and amber chips. It's not equivalent, but again, it gets into, are you okay with that trade-off? So one big trade-off here is, if you can imagine, if I were to, let's say I want to create more and more different colors, that means I need to have a larger diversity of chips, and that means I have to pack this larger diversity of chips into the small package, like we mentioned. It still has to be for now, so I still have to pack it in. That becomes a bigger problem because now I have to do what's called color mixing. I don't want to see the individual the reds and the greens and blues. I want it to, when it comes out of the lens, I want it to be a uniform white. I don't want a single shadow. I don't want fringing, right? And so as the trade-off that we're running into is, as you add more and more colors, right, to the spectrum, we're talking about filling in those spikes with a lot of little spikes, right, just so that it looks more continuous. What that means is that we're going to have to take up real estate on the actual LED package to do this. And so that's going to make sources bigger, or either they'll make them too big, or what's going to end up happening is that we're going to have to deal with some other color mixing issues. So that's kind of, I think that's the balance that the manufacturer and the users have to kind of have to weigh. It's whether or not they want all this full color at the trade-off of potentially there's going to be like, you cannot fit that many chips into such a small package.
But what if you just went to a tungsten phosphor? You just created a tungsten.
Yeah. So if someone wanted a single tungsten, and there are fixtures that do that, you could very efficiently make a single non-color tunable like kind of tungsten-based LED fixture, and that's actually how most of them started. The challenge is that you either have to build a fixture that has no color shifting at all because you have no other chips to kind of mix in with it. Right. So that's one approach generally, or you have to mix in like some sort of small compensation. Yeah. Nowadays, our experience has been that the white spectrum is kind of taken for granted. It's a given, and then more emphasis is placed on, can it do effects and things like that, which has its merits too. But I think the white spectrum is recently been basically, it's assumed that you can already produce a pretty good spectrum with a pretty good fidelity, CRI, all these things, And especially if people are looking at these things through cameras, again, a lot of the information that we see by eye is actually not captured by the camera. And so that gets into whether or not it actually matters. I mean, I think that's a little bit more of a subjective question,
Yeah, but everybody always wants everything.
Wait,
keeps us busy.
What about now? This is probably a absolutely stupid idea, but was there any possibility in the future that you'd be able to change the chip that you have in the light source? So just like you used to change a filter, would you be able to take that sort of LED array out and put in a different one?
Yeah, and that's been an approach. I would say one easy example of that is my kitchen, in which my contractor installed a very 50s. It was a little bit too daylight for my kitchen, and then I went in and switched them all out. So it was the same fixture. I just changed out the LED bulb. So the short answer is yes. There are cases where you could do that. On the fixture itself, I think within LED fixtures that we see used specifically for film, I think that's very challenging. And the reason is because once we start changing out the LEDs, we need to start changing out the calibrations that are associated with the LEDs. Okay. And also, it's not just the LEDs, it's the heat sink, right? It's the electronics that go with it. So when I think of LEDs, I tend to not think of just the individual chips. I think of what's the minimum set of electronics or housings, whatever it is, to be able to accurately power that. And there are some manufacturers who early on tried to switch out just the LED chips. I would generally say it wasn't very successful. And then more recently, manufacturers who've been looking at changing out the LED engine to have different colors. So you can have like a daylight engine and then like a color engine, things like that. From what I know, it hasn't been particularly popular because, again, this trade-off is that, practically speaking, if I can, even though you might get maybe a little bit more brightness, or maybe the color fidelity is a little bit better if you use like a pure single color phosphor, it's not worth the trade-off of having going through all the effort for that extra little bit of fidelity. And so I think it gets down to like a kind of more of a practical, like an operator question, and sometimes budget too.
Right.
So
Yeah. Always that.
I think the way you've concentrated on your lens of Fiilex, that is, concentrated on the Fresnel lamps, but then have a range of Fresnels that you can put in front, or a range of different soft boxes or lenses that you can put in front of the same reflector. I think that's very, very astute.
Thank you.
Design.
Yeah, but when we were looking at, it took me a while. I still don't remember the names of all the juniors, the tweenies, the in-betweenies, and things like that. But what we wanted to do, again, was to build sort of the LED analog of what filmmakers are used to, right? They have a lineup of tools they use for different sizes, for different applications. We wanted to be basically, I don't want to say exactly a one-to-one swap, but it basically to give them a tool and a form factor that they were very familiar with, right? And so developing this, we had to be able to make fixtures that are small, which has its own set of challenges, to fixtures that are large. Our early fixtures, actually, it's funny. We actually started more, Fiilex at least, started more with the kind of the on-location E&G kind of news crews. And so we were very used to building like very compact, weatherproof fixtures. And it was only when we entered the film where we started to have to build like kind of larger, we're talking like 10K equivalent, 20K equivalent, tungsten equivalent at least. And what's sort of evolved over this time is like, obviously the lenses have gotten bigger and we've had to create a whole lineup. But even the way you mount these things, the way you safely hang, like all these things start to become factors. And so, it's been a learning experience. Yeah.
Well, and you've no idea where it's going to go next. The biggest development. Yeah,
I mean, for LEDs, I mean, we'll probably continue to see larger, more powerful, like even Fresnels. I don't think that's maxed out yet, but I think you mentioned earlier, Roger, it's like, the trade-offs are starting to appear, and one of them is noise. It is very challenging to make these large sources while keeping the fans at a reasonable level, right? And so I think there's still space there, but we're starting to reach them. And then the alternative that we see is, again, for people who want to get more and more light, it's really just but it's to be able to tile them together to create these like larger sources. They can still be very punchy, especially if you're like shooting through windows or off like big bounces, things like that. I think that's a great application. But once we get into, I want to be able to, get into like new technologies. Like for instance, lasers are one example of that. I think that's a TBD, to be seen, to be determined. Yeah. Again, it will come down to the trade-offs. Like when the new technology comes out, are we gonna be willing to give up what we're already used to and we're comfortable with, right? Everything's going to come with a trade-off. Yeah.
Well, this has been great.
Thank you.
I mean, really
enlightening,
informative.
Yeah.
We really appreciate you taking the time to do it.
Oh, no, thank you. Yeah, it's really fun to talk about.
Certain instances, I'll still stick with a maxi brute or 18 light maxi. Yeah. I don't think there's an equivalent yet, but I'm looking for it.
And I do like that where. Just because technology will continue to improve, and there are certain areas in which I think it's a little bit of a no-brainer to use an LED versus. But there are many situations in which, like, the question is like, why are people still using tungsten? I think that question is. It's a little bit charged because the reality is that there are a lot of factors that go into these decisions, right? One of them is familiarity. One of including like, is your crew even trained with this new technology, right? It's something that when we're designing fixtures, I'm not trying to create something that's going to require years of experience and certification to operate, right? And then second thing is budget, right? And there are a lot of tungsten fixtures out there that are perfectly good and perfectly usable. And in that kind of situation, maybe it makes more sense to use tungsten. So even coming from LEDs ourselves, like it's a great tool, but it's not for every situation, right? It really depends on what you're trying to do.
Yeah. It's also we've been to a number of film schools, and you find that they've got a lot of tungsten lamps.
Yeah.
Because they've been given a lot of tungsten lamps because it's cheaper, and certain rental houses have been swapping over to LEDs, and they've given away their tungsten sources. So their students really aren't getting the full education on LEDs and the possibilities and what the range that a company like yours has.
And I think that's something too. It's like, because we're starting to see more LEDs even in our day-to-day lives, And the cost has really come down quite a bit. I mean, maybe they're not in the exact same form factor with the same controls sophistication that we have in set lighting, but in day-to-day life, we're starting to see more LEDs. And so the good news is that the general public is getting more and more familiar and comfortable with LEDs. And I think that because the cost is coming down, we'll see more and more LEDs going into schools, and I think that's the necessary. At the same time, our parents were a little tough around me, but they always think, when you're in school, do it the hard way. You gotta start doing it the hard way first before you get.
Well, it's like learn on film first before you shoot digital.
Exactly. So
yeah, very good.
Well, thank you.
Thank you so much for this, Jeff. It's been really good.
If you'd like to sponsor the Team Deakins podcast, let us know at pod@teamdeakins.com. Thanks for listening. If you want more information and further discussion, check out the forums at www.rogerdeakins.com. Becoming a member is free, and you can ask follow-up questions there. And be sure to subscribe to the podcast for more new questions and topics. Also, check us out on Instagram at team.deakins. See you next time.